Okay, the next item in this chapter is electrophysiology of neurons. So again, electrophysiology means electricity. We already talked about that when we were covering the muscles. Is the same. I shouldn't have said same. It's similar. Okay, again, we are talking about electrical potential, current, polarized, voltage. Okay, similar concepts. So we are not going to talk about much about it because we already mentioned that. For example, resting membrane potential, we said in the case of the neuron is -70. We say in the case of the muscle is -90. Let's keep scrolling down. The main ions involved on this are sodium and potassium. We already mentioned that as well. So we keep scrolling down. That's just history. We already mentioned extracellular fluid, intracellular. We said the most important ion outside is going to be sodium. Most important inside is going to be potassium. Again, once you receive the stimulus, remember sodium channels open. The sodium goes from the outside extracellular inside to the intracellular area. And because of that, the polarity is going to change, right? It's going to change from -70 to +35. Eventually, once +35, potassium will come out and that will return the membrane, the cell back again to the resting potential. Now we have local potentials. So local potentials, we say they start, right? But they don't reach the trigger zone. Therefore, those are weak stimulus because they are not strong enough in order to reach the trigger zone. Not only that, they can start and stop. And they're reversible because you will start over again. Okay, so let's keep going down. So again, you have in here the stimulus, the sodium goes in, but it's not strong enough in order to produce an action potential. So let's keep going down. So this is local potential. So right there, what are the characteristics for local potential? They are decremental, right? They start, but then they don't reach the trigger zone. They are graded, they are reversible. Those are characteristics of local potentials. They can be excitatory or inhibitory, okay? And right here you have a nice table where you can compare action potential and local potential, okay? But main thing is the local potential is not strong enough to reach the trigger zone. So they are decremental, meaning it starts strong, but then it gets weaker and weaker and weaker and doesn't reach the trigger zone action potential. Once the stimulus is strong enough, it reaches the action potential and the action potential cannot be stopped. Okay, you can look at this table and pay attention to the differences between local and action potential. Action potential, that's what we have been talking about so far, potassium, sodium, and the depolarization and the repolarization, all those things. So right here we have the table, this particular graph again. So we said action potential, resting potential, depolarization, repolarization, action potential. Okay. Yeah, I can use this figure to talk about the sodium-potassium pump. Depolarization is because sodium goes inside the cell. Repolarization is because potassium comes out of the cell. If you really think about it, if potassium is going to constantly be leaving the cell, so eventually the cell will run out of potassium, right? Because the potassium is constantly going out. Not only will the cell will run out of potassium, but it will be filled with sodium. But that's not what you need in order to initiate the action potential, because we said that it initiates with -70, which is the resting potential, and having a lot of potassium inside. So then, since the potassium leaves, you don't have a lot of potassium inside that neuron. So then, how will you start this new resting potential right here? Well, what happens is that sodium-potassium pump is the responsible for that. Sodium-potassium pump will take the potassium out of the cell, pumping it outside the cell into the extracellular fluid, and it will take the potassium back inside the cell. So then the reason why this mechanism works over and over and over again, back and forth, back and forth, back and forth, is because during the action potential, the sodium goes in, the potassium goes out. Why the cell does not run out of potassium? Because the sodium-potassium pump is going to pump the potassium back in to the cell, and the sodium will come out. Okay? That's the function of a sodium potassium pump that makes this mechanism to happen over and over again. Okay, let's keep scrolling down. So here they are explaining how that happens, which I already covered many times. Polarization, depolarization. Let's keep scrolling down. Right here they are showing you that negative 70 channels are closed, but what happens then? This negativity starts to becoming positive because sodium starts going inside the cell up to positive 35 more or less. Once it reaches positive 35, then these channels sodium close, channels for potassium open, potassium starts coming outside the cell, and then this goes back down again to negative 70. That's what we call repolarization. Okay, so I'm not going to explain much time on that. Here are characteristics of the action potential. So we said this is all or none law, meaning once it starts, it starts. You cannot stop it. Okay, non-decremental, meaning once you start, you cannot stop that again. It doesn't reduce the stimulus, or it doesn't decrease the stimulus. And the action potential is, again, irreversible. Once it reaches the action potential, it will continue until it stops. Okay, until it reaches the end of the neuron. Refractory period. This is fairly simple to understand. Right here you have the action potential again, depolarization, repolarization. As you know, two things cannot occupy the same space, basically. All right, so if this is one action potential and you use this to grab a pen, right? So this action potential makes you move your fingers and you grab a pen. Can you grab the pen again during the same time? No. Once you grab one pen, it took you 5 seconds to grab the pen. Those 5 seconds already passed. You cannot grab the pen again during those 5 seconds that already passed. So basically, that's what it says in here. This is called the refractory period, because once you have a stimulus, the stimulus continues, and what it says is it's called absolute refractory period because you have one stimulus right here and another stimulus cannot happen at the same time. There's something else called relative refractory period. Okay, relative refractory period refers to this part. You see the yellow column right here? Okay, this is negative 70. This is the resting potential. However, as you can see here, when the potassium starts coming out, so you can reach the negative 70, a lot of times the potassium, the channels keep open even though you already reached negative 70. So the potassium going out overshoots the negative 70 and goes even beyond that. So let's say this point is negative 80, more or less at this level, right? Negative 80. Right here. Okay, so let's assume this is negative 80. This point right here is going to be negative 70. So we know that an action potential starts at negative 70. However, the theory says that if you have a stimulus that is very strong, you can start an action potential right here when it is not the resting potential. So when you start an action potential in a point which is not negative 70, you will start it in this yellow area. Therefore, that's why it's called relative refractory period, because you can initiate it even though it's not negative 70.